Hello, everyone. So my name is Evan Laufer, and I'm a PhD student here at Stanford. And I'm going to be talking about our paper, ZK-Pi, Proving Lean Theorems in Zero Knowledge. And this is work that I did with another PhD student, Alex Ozdemir, and Dan Bonnet. So before we dive into any of the details, let me give a bit of a motivating problem for why we set out to do this. So of course, as we all know, all unverified software is going to have bugs. Some of these bugs might be mild, but other ones might cause severe security vulnerabilities. And so because of this, there's been a recent line of work where we want to prove that a piece of software is secure. The goal of that line of work is to use a tool called a theorem prover to actually prove that the software is secure. And all a theorem prover is a tool which will check a mathematical proof. If you know what Coke or lean are, these are examples of theorem provers. How do these get used? Well, first, the programmer will encode the software in some way into the theorem prover. That might be actually writing the software in the theorem prover itself, but you could also imagine encoding the semantics of a higher level language like C and then proving things about the program. Then the programmer will write a proof that the software is secure. And then the theorem prover will actually check the proof and guarantee that it's correct. So you have very, very high assurance that your software is bug-free. Of course, there is a problem here, which is to check the proof, the user actually has to have the source code. So we could imagine maybe I want to get a binary from some company or somebody who's untrusted. Just with the binary itself, I can't actually check the proof. I'm going to need to have the source code or some encoding which describes the inner workings of the program at a high level. Obviously, this is unacceptable for proprietary code. So the core question of this work is, can we actually prove that the source code is secure without actually revealing what the source code is? To give another problem which motivates this is proof of exploit. Given the source code of a program, can I generate a proof that an exploit exists? One idea here would be, once again, we encode the software in a theorem prover, and then we can write a mathematical proof that the source code actually has some vulnerability. This might be useful for things like bug bounty programs, where I actually want people to find exploits and tell me about them. What are some problems here? Well, one is that these proofs might be large. So can we make them small, say constant size? And then another question is, maybe I don't want to reveal the exploit before some payment is initiated, right? So again, can we keep these proofs private? So what is our goal for this project? Our goal is a ZK snark for lean theorems. So just to give a high level of what that means, we're going to have two parties, a prover and a verifier. The prover is going to have two inputs, x and w, where x is a lean theorem statement. Say p and q implies q and p would be an example of a theorem that I might want to prove. And then they'll also have w, which is a secret proof that x is true. P should be able to generate some short proof pi that they can send to a verifier v. And then v should be convinced by pi that x is true while learning nothing else about the witness w. Now, we could imagine going about this by designing a whole new proof system from the ground up. But for this work, we decided to go with a different approach, which was using generic ZK snarks for circuit satisfiability in order to do this. And then now our goal becomes writing a circuit which checks lean proofs. So here, now instead, we would have some sort of arithmetic circuit. So this would be consist of multiplication gates and addition gates. And again, this would take in as input our lean theorem, x. It would also take in our proof, w. And then we can just use a generic snark like Gross16 or Planck in order to create our short proof pi. Oh, what? Sorry. Let me go back. Here we go. OK. So just as an overview, what do we do in this work? So we implement ZK-Pi, which is the first implemented ZK snark for lean theorems. And as part of this, we talk about techniques for building a ZK snark with typing and materialized judgment trees. I'll get into what this means in a second. We also have extensions for key lean features like dependent typing and inductive constructions. And also we have some data structure and type system optimizations, which I might talk about a little bit in this presentation. So before I get into how we build our circuit, let's just talk about how lean actually checks a proof itself. Well, here's an example of a lean theorem. We can see here the theorem statement once again. This is the thing that we want to prove. And then we have the actual proof of the theorem. I've elided a few details here, but you can kind of get the idea. And what lean does actually to check this proof is it uses something called the Curry-Howard isomorphism. All the Curry-Howard isomorphism says is that proof checking of mathematical proofs is actually equivalent to checking that there exists some expression of a particular type in some type system. Right? So by type system, I mean like, for C, we have a type system where we have, say, integers and strings. Well, of course, this type system is going to be much more complicated, but it turns out we can actually do theorem proving by just checking the types of expressions. To give a little bit more intuition here, hopefully, we could imagine, or here's an example, which is that logical implication can be represented as the type of a function. Right? So here, if I wanted to say P implies Q, I can express that as the type as a function which takes in a proof of P and produces a proof of Q. Right? And then here, our proof would actually be the implementation of this function. So what is lean's type system? Well, they use something called the calculus of inductive constructions, some scary words. But I don't want to get into the details of lean's type system for this talk. If you know lambda calculus, it's kind of like that. But we're just going to go over our techniques over a simplification, which is we're just going to talk about something like a C-like type system. So maybe I have statements like len s plus 1 is of type int. And most of our techniques actually don't rely on the specific details of lean's type system at all. So we'll be able to talk about most of the stuff without going into all of those details. So just to get back to our big picture here, what we do is we take our lean theorem and proof. We convert this into a typing relation, which then we convert to a circuit satisfiability relation, which we can then use a generic snark like Planck or Groth to create our zero-knowledge proof. And then real quick before we dive into the details, again, like why is this even hard? Like why do we even care? Or why am I giving a talk about this? Well, type checking is fundamentally this recursive operation. And if we just naively express recursion in a circuit, it's going to be very expensive. Why is this? Well, when we encode a control flow in a circuit, we end up actually having to take every path. Right? We don't actually know which path we're going to take. And so we end up having to write down both. What this ends up looking like is exponential growth in the size of the circuit as we grow our recursion depth. So here the kind of the outline of how the talk is going to go. The first is how do we actually represent the terms and types from our typing system as inputs to the circuit. And then we'll talk about how do we actually check that a particular term is of the correct type. So first, representing terms and types. The way that we do this is we basically just convert it into something similar to an abstract syntax tree. So we could imagine here if I have a function which takes in a string and returns an int, and here's the body of the function, which is just len s plus 1. We can convert that into a true representation, as I said, similar to an abstract syntax tree, where the root is going to be this function declaration, and then its children are going to be the body of the function. Right? And exactly what this tree looks like depends on what types of terms exist in our language. But we can write out this tree, and then we can just flatten it into an array and pass that in as the input. So right here's an example. We just take every node in our tree, we put it inside of an array, and then each node in the array will also have a pointer to its children nodes. All right. So we've successfully encoded our terms and our types. And here's to even be more concrete, we can see a code snippet that might represent this, where we have, say, a term struct, which has some kind, maybe it's a variable or a function definition, et cetera. And then it will have some index to its left child and its right child. So we'll just take an array of these structs and pass it in as the input. All right, so now we actually need to check, okay, how do we know that this term is of the correct type? Well, let's step through a little bit of an example of the types of things that we need to look at in order to check this. So here we have len s plus 1 again, and what we want to do is check that this is of type int. Well, to check that this is properly typed, we're going to need to check the type of all of the terms that make up this expression. Right? So first, we have our plus operator, of course, which should take in 2 integers and return an integer. We also have len s, which should return an integer, and 1, which should be an integer. And I've colored these boxes to show what we need to check equality for, right? Len s better be an int because plus expects the first operand to be an integer as well. Then we have to recurse, right? We need to check, is len s actually an integer? Well, how do we do that? We can, again, break it up into its component parts and see that len s is a string, or a function from string to int, and s is a string, so everything matches up here as we expect. Now, this type of tree, if you've taken a programming language class, you might know as something called a judgment tree. And we would call each step here one judgment, right? So just this step from len s plus 1 to its component parts is called a judgment. Now, how does this help us actually write our circuit? Well, our idea is let's just have the prover create this tree, and then we can write it out as an input to the circuit. Right? So here we take our tree, and we'll just, once again, encode it in an array representation. So each judgment will go into a single node in this array. And then the judgments will also have pointers to the judgments they depend on. Right? So here, len s plus 1 depends on the type of plus. So we just have these pointers, which point in the array to where we need to go. To be more concrete again, I could write this out as a struct where we have, say, some kind of judgment. We also have a pointer to the term that we're typing, the type of the term that we're asserting. And then we also have these pointers to these judgments. And note, I write this pointer syntax here, but really these are just indices into the corresponding inputs, the arrays that hold these inputs. So let's just quickly step through how do we actually check this tree now that we have this array. Well, now it becomes actually very simple, right? What the circuit's going to do is it's going to iterate over this entire array, and it's just going to check, do these equalities hold? It will check, is this the return value equal to the return type expected from plus, right? And so once it checks this particular judgment, it'll move on to the next one, right? And notice here, as we step through this array, we're basically implicitly checking the entire tree, right? So all of a sudden, we've gotten rid of our recursion problem because we've just flattened it out into an array. So that's great. Now, something else that comes up here is while we're checking these judgments, we have to look up a bunch of parent judgments and terms, right? But something that's important here is that the actual array indices that we are checking depend on the value of the judgment. And so these actually must remain hidden. The circuit doesn't know which indices it needs to access until we actually run the prover, right? To give an example of some intuition of how this would work if we're doing this naively, we're basically going to have to encode in the circuit this big expression here where we say, OK, if my index equals 1, then we return the first element, or 0, then we return the 0th element. If it's 1, then we return the first element, et cetera, right? So we end up with this O of n cost based on each time we access these arrays. So as a whole, our circuit's going to end up being O of n squared, which is not very efficient and not what we want. So to get around this, we use techniques from random access memories, or RAMs. So what is a RAM? Well, a random access memory is just a data structure where I have 2 operations. I can read from an address, and I can write to an address. Great. And there's a lot of prior work on representing RAMs efficiently in ZK snarks. Why do other people care about this? Well, somewhere where RAMs come up as well is if I want to, say, prove the execution of a CPU architecture, that also needs to access some sort of memory at prover-defined locations. And so we have this same problem. So really, we just take work that already exists and mold it to our application. I'll quickly go over exactly how this works. So this prior work is representing a RAM efficiently. How do we do this? The idea here is that the prover will provide a trace of the RAM accesses, and then the circuit will just check that they're consistent. What does it mean to be consistent? Well, any time that I read at an address, it should return the last value that I wrote to that address, right? So here we can see a table which represents what is a trace. So each access will have a timestamp. It'll have an operation, an address, and a value. Here we can see at time 1, I write 0 to address 0. And then at time 3, I read from address 0, so I should also get back 0 again. Right? If my access at time 3, my read of address 0, ended up returning 1, we would say that this is inconsistent. So the circuit should throw an error. So something to note here is that when we sort our trace by time, once again, we run into this problem where all of a sudden, when I'm checking that this read at time 3 is consistent, suddenly I need to look somewhere in the array, but I don't know where in the trace I need to look. Right? Which row am I supposed to look at for time 3 to find the right that I'm supposed to correspond to? But something to notice is that if we instead sort the trace by address, this check becomes really easy. Right? We just always look at the row right before us, and we should check, if I'm reading, that value should be the same. So the idea from this prior work is the prover will give both a sorted trace by time and an address sorted trace. And the circuit will then check, 1, is the address sorted trace correctly sorted, and is it consistent? Right? We said that this is easy for the sorted trace. And then it will check, do both traces actually contain the same rows? In other words, are they just reorderings of each other? To do this, we use something called a permutation argument, or a permutation check. So if we consider 2 tables, T, so this might be our time-sorted table, and A, which is our address-sorted table, it turns out that for a randomly sampled alpha and beta, we can just compute this value, this big product. And it turns out that if T is not a permutation of A, then the hashes of them will be different with overwhelming probability, assuming that alpha and beta are sampled randomly. So how do we use this for our random access memories? Well, our circuit is just going to do this, right? It'll just compute these hash functions and then check if they're equal. Note here is that the circuit actually needs access to these random values. And so we use, instead of using Gros16, we use a proof system called Mirage, which is basically just think Gros16, but it has access to random values inside of the circuit. All right, so I've covered a lot of stuff here, and but there was something that I kind of shoved under the rug when I was talking about our type system, which is how do we deal with variable bindings? Right? In most languages, and indeed in Lean's type system, we have variables where I can bind a variable to a value and then use it somewhere else. Right? So maybe I have an expression, let x equals 4 in x plus 5, and I want to prove that that's of type int. Right? As I'm checking this, somehow I need to remember, is x of type int or not? Right? So we have something called a context, which just tracks what the type of x is. And as we walk up this tree, we're going to keep track of the context. And then over here, when we actually need to get the type of x, we can just look it up inside of the context. So this is great in like the traditional computation setting. But inside the circuit, now we need to also have some sort of representation of these contexts. Well, what are the contexts? These are key value maps. And we need them, again, to be efficient in this circuit model. The number, length, and the values in the context should remain hidden. So we have some strawman idea, and we'll see the problems and how to fix it. Our strawman idea is just going to be a linked list, and we'll once again store it in a RAM. So the prover will provide these contexts as part of the input to the circuit as well. Insertion, something great about this, insertion is very easy. Right? If I want to insert a new key, say I want to say that E is of type string, well, then I just put it inside of my linked list at the head, right? So this is a very easy operation. And looking up what the type of E is, as long as it's the head, is also very easy. But things get a little complicated once we need to start looking up something that's further in the list. Maybe I need to look up the type of A. Well, now I need to walk the entire list. And once again, we run into this problem, right? Inside of the circuit model, we don't actually know if we're looking up A or we're looking up E. So we basically need to pay the full cost of walking the entire list every single time we do a lookup. So that's not really great. How do we get around this problem? Well, our idea is, what if we just say anytime you do a lookup, the value you're looking up better be in the front of the list, right? So let's go through an example to see what I mean. Let's say that we have this context, which already contains that x is of type int. And I want to type this statement, let y equals a in x plus 5. Right? So here, y doesn't matter at all, but we're going to add this new binding. And as we try to type the sub-expression here, we've added y to the front of our context list. So what we're going to do is we're just going to say, OK, we get to having to type x. We're just going to say, you better put x in front. Right? Now looking up becomes very easy. And now what do we need to do? We need to check, does c prime equal c double prime? Are these lists equivalent except for ordering? Well, luckily for us, we just talked about a nice argument that we have where we can check if two things are permutations of each other. So we're just going to use the exact same hash function that we did before. Right? So now our linked list will also carry with it a hash, which is this, this special hash function of all of the elements in the list. That way, when I actually want to check if these contexts are equal, all I have to do is check if these hashes are equal. And so this becomes very inexpensive. Here, once again, we have some example code if you're into concrete details, but this isn't super important. So once again, I'll just return to kind of the big picture here of, we have this lean theorem and a lean proof. We've converted it to a typing tree, which then we can convert into a circuit satisfiability relationship, and then we can convert that into a zero-knowledge proof. OK, so I've talked a lot about the details of how we implement this, but we actually did it. We actually implemented it. And what is the efficiency? Well, here's 3 example theorems that we proved. The first one is De Morgan's law. The second is the pigeonhole principle. And the last one is the correctness of an insertion sort algorithm. Now, of course, our efficiency could be improved. So we see here that for our most complicated example, the correctness of an insertion sort, it takes a long time, 10,000 seconds. Now, one thing to note here is for this insertion sort check, we prove everything from first principles, including statements like, if I swap 2 elements in a list, well, the list doesn't change what is inside of it, right? So we're proving everything from first principles here. But you could imagine instead having some, say, standard library of assumed facts that we know about math. Maybe if I swap 2 elements in a list, that the elements in the list don't change. But we didn't do that just because we wanted to see what are the limits of the system. And also, I will say these numbers are somewhat out of date. It turns out that a lot of this proving time ended up being some efficiency bugs in our compiler that we were using. So I think we were able to get insertion sort down to maybe like 1,000 seconds or 2,000 seconds, which is about a 10x improvement just by fixing our compiler. So that's it. In conclusion, ZK generates zero-knowledge proofs of lean theorems. And here's a link to our ePrint if you want to read the full paper and the full details of the type system. So I'll take any questions.
Question?
Yeah, the question was, how does this compare to running lean in a ZK VM? We haven't actually tried that, but I would imagine that we would end up with significant overhead just because as soon as we start putting in things into a ZK VM, we're basically taking the C code for the verifier and converting it into multiple instructions, whereas here, you can almost think of this as like a tailor-made VM for lean type checking, right? So we imagine that it would be more expensive, but we haven't actually tried to do it. I certainly think that if you took just the lean verifier and tried to run it in a VM, you wouldn't be able to prove anything just because the lean verifier itself is somewhat large. But that's an interesting direction for future work to see how it compares.
Question?
Yeah, I think the question, correct me if I'm wrong, was are there applications here for proving things about AI models? Certainly, you could prove things about AI models here. I'm not entirely sure what types of applications you would need where you want to keep the proof private, but maybe you might want to prove something about a model that you aren't releasing, and then you could use this. I'm not sure how the efficiency would go, because once again, if we have very, very large models, the encoding of that into a proof is also going to be pretty large. Yes, so of course, anytime you're going to be making, say, a proof that formally verifies a piece of software, you're going to have to say, what types of things that you need to guarantee. So, part of that would be a public statement which says, like, maybe I want to prove that my software isn't going to access your secret files or something, right? Of course, that's going to have to be upfront, and it could be the case that I fail to list out everything that I care about. So that is one issue. Actually, part of the reason I say this is an important step is I kind of glossed over something important, which is if I'm sending you a binary, I need to compile my source code, right? So there's going to be this step here as well where, if I'm sending you a binary and a proof, there needs to be a linkage between the binary and the source code, which I'm writing the proof about. Yeah, hopefully that answers your question.
Awesome. Thank you so much, Evan.
Thank you.